So now we want to calculate the work associated with the weight of the body. And here we are assuming a constant g. So work done by the weight mg of a body is the body is displaced from an arbitrary altitude y1 to final altitude y2. So assume that you move the body from y1 position, which is the y position of the particle, and then you move it from this position to somewhere this position 2, and the altitude of 2 is this y2 here, and you are interested to calculate the work done of the weight of the body. So here we are not interested to calculate the work done of some other force, but we are interested to calculate the work done by the weight of the body, which is mg. And again, if you look at this r, which is the displacement, can be split into two components. So x component and y component. So the y component is in the vertical direction, which is this direction here, and the x component is the horizontal direction, which is this direction here. So as we already know the equation of the work, that is u12, which is the work done by a force from 1 to 2, and which was s1 to s2 ft dt. So ft ds. So in this case, ft is the tangential force, or the force in the direction of the displacement. So in this case, because we are interested to calculate the work done by weight, we want to calculate this work done by weight mg. So therefore, what we can write that u12 should be equal to, so in this case, because mg is in the downward direction, and dy is in the upward direction, and dx is in the horizontal direction. So we know that the mg and dy, the mg is only the displacement in the direction of the force is dy, and dx is not in the direction of the force. So therefore, we will just take dy here. So this means that we will just take s1 equal to y1 and s2 equal to y2, and then you will have mg, and you will have dy here. Because we are interested here to calculate the work done by the weight of the body, which is mg. And if you look at this figure, so mg is in the downward direction, dy is in the upward direction. So this means that both are in the opposite direction, and you should also put a negative sign here. Okay, so if you just look at this integration here, so mg is constant, which is not a function of dy or y. So this means that you can take this out of the integration. So it will become minus mg, and then it will become y1 to y2 and just 1 dy. So if you just do the integration of 1 is with respect to y is just y here, and it will become y1 to y2. So minus mg, and then it will become y2 to y1. Okay, so now in this case, if you look at this equation here, this is the work done by the weight when the body moved from position 1 to position 2. So if you look at this equation here, this term, which is mg into y2 minus y1, and because y2 is greater than y1, so this term is positive, and we have a negative sign here. So because the body is moving is against the gravitational force, so therefore the work done is negative, because you are moving the body in the opposite direction to the gravitational force, and therefore you are getting a negative sign here. Okay, so now we can derive another important principle here, which we will be using for the solution of kinetics problem, and this is work energy equation. So now we already know that the work done by F during movement of the particle from point 1 to point 2 which we derived in the previous case, was U12, and which was S1 to S2 and FT ds. So this was the definition of the work. So now in this case, what we're doing here, that if we substitute the Newton's second law, because we know that the force is equal to ma, so this is the Newton's second law. So if the force is tangential force, then the acceleration will also be a tangential acceleration. So if we just replace this equation in case of ft, so then the u1 to 2 will become equal to s1 s2, and then it will become mat ds. So this is how we end up with this equation here. Okay, so now if we use this well-known equation that we derived in the first lecture, that a dv a ds is equal to v dv. So we derived this equation in the first lecture. So if you are not sure, please go to the first lecture and watch it again. So a ds is equal to v dv, which is simple to derive. So if we just replace this ads by v dv, so this ads we can replace this ads here. So we can replace this by the v dv. So then you can write that u12, which will become equal to integration and then m, and then it will become v dv. Okay, so now in this case the integration was with respect to displacement, so the limits were from s1 to s2, but now the limits now the integration is with respect to velocity. The limits will become v1 and v2. Okay, so now if you integrate this equation here, so we know that m is constant here. So if you take m is constant, then the things which will left inside is v, and the integration of v is v square divided by 2, and then the limits are v1 v2. So if you just put the limit of integration, so you can just write this half m and then v2 square minus v1 square. So you will end up with this equation here, that u12 become equal to half m v2 square minus v1 square. And now you may have seen this definition of the kinetic energy. That kinetic energy, here we represent the kinetic energy by T. Of a particle is defined as this. So T will become, which is the kinetic energy of the particle, is half mv square. So now in this equation here we have half mv2 square and half mv1 square. So this means that the if we just replace T in this equation here, so then this u12 will become equal to half mv2 square and minus half mv1 square. This will become T2 minus T1. So T2 is the final kinetic energy of the body, and T1 is the initial kinetic energy of the body. So we can also write this delta T, which is the change in kinetic energy, which is T1 minus T2. So we derive this equation, that is u12, which is the work done of the force from 1 to 2, is equal to T2 minus T1, which is equal to delta T. So this is the equation that we derived here. Okay, so now the work energy equation for a particle, which we derived just now, was this equation here, which is T2 minus T1 equal to delta T here. So you can say that in words, that the total work done by all forces acting on particle as it moved from point 1 to point 2 equal the corresponding change in kinetic energy of the particle, so which is this equation here. Now work always results in change of kinetic energy, so you can also write this equation in this form, that if you move this T1 to this side here, so this will become T1 plus U12 equal to T2. So in this case, what you can say that the initial kinetic energy plus work done on the particle is equal to the final kinetic energy of the particle. Okay, so now this equation is what we call is the work energy equation, or the work energy principle. And you will be using this equation to solve numerical examples. But again, the question here is that why we need this equation, and why we don't want to use the Newton's second law to solve directly the problems. So the advantages here is that it avoids the necessity of computing the acceleration and lead directly to the velocity change as a function of the forces which do work. So in case of kinetics, you always need to calculate the acceleration, which is F is equal to ma. So F is equal to ma. So you always need to calculate the acceleration to solve the problem in the previous case. But now in this case, you don't need to calculate the acceleration. You know that the if you can calculate the work, and we know that this is just half mv v1 square, and this is half mv2 square. So you can directly solve the problem. So you don't need to calculate the acceleration now. And so this is just about the application of this this principle, that the resulting equation will be useful for solving problems that involve forces, velocity, and displacement. So if you have to deal with only with forces, velocity, and displacement, so then you can just use this equation instead of the solving for the acceleration, which you were doing in the previous lecture. Okay, so now we can also further simplify this this principle. So for that, we will need to define potential energies here. So the first one is gravitational potential energy. So gravitational means it is due to the gravity. So gravitational potential energy, which is you can represent by Vg of the particle, is defined as a work mgh done against the gravitational field to elevate the particle a distance h above some arbitrary reference plane, which we call datum, and where Vg is taken is 0. So a datum point, which is this point here, if you take this is our datum point where the Vg is 0, which is the gravitational potential energy. So if you take the gravitational potential is 0 here, and you move the body from this location to this location here, and the weight of the body is mg, the height between this location and this location is h, which is the vertical distance. So as we derived in the previous case, that if you move the body from this location to this location here, so in the previous case, if you take this is our y1, and you take this is our y2, so we derive this equation that the work done was equal to minus mg y2 minus y1. So this was the work done when you move the body from y1 to y2. So we derived this equation previously. So in this case, as you can see that if you take y1 equal to 0 here, so u12 will become equal to minus mg, and then y2 minus y1, which will become so if you take this is our 0, so then y2 will become our h here. So then y2 minus y1 is equal to is h here. So then minus mgh. So then the work done from if you take this is our h. So then if y1 is equal to 0 here, if we take this is our 0, so then y2 will become equal to h. And then this work done when you move the body from this position to this position is mgh. And obviously this is negative because this work was done against the gravitational force, and we know that this work will store in the body in the form of potential energy, which is this Vg, and therefore then you can write the Vg, which will be equal to mgh. So this work that you've done against the gravitational force, which was negative, will store in the body in the form of energy, and this energy will be positive energy. So this means that the body is now able to do some work because it is at this height here, so it can move down without any force because it has some energy now. So similarly to the gravitational potential energy, we can also calculate the another sort of energy, which is what we call is the elastic potential energy. So the elastic potential energy is due to the spring force. So if you consider this figure here, which we discussed earlier, so the work which is done on the spring to deform it is stored in the spring and is called its elastic potential energy, and we will represent this by VE. So elastic potential energy of a spring is the work done on it to deform it an amount x. So in the previous case, we derived that if you move a body from a body of mass m, which is attached to a spring, and if you move this from x1 to x2, so the work done will be equal to, which was, we derived this equation that k x2 square minus x1 square. So this was the work done when you move the body from x1 to x2 and it is attached to a spring. So you the work done is of the spring force is shown by this equation here. But now if we just take x2 equal to, if you take x1 equal to 0 and x2 equal to x here, so then this u12 will become equal to minus half k x x square. This means that the if you move the body from 0 to x, and x is again the stretch in the spring here, or it can be compression in the spring. So if you move here, what will happen, that the you are working against the spring force, and therefore it is a negative sign is here. But as you can see here, this negative energy will store in the spring in the form of its potential energy. So then we can write that the VE, which is the elastic potential energy, will become equal to half kx square. So this is our elastic potential energy here. And again, the this means that now the spring is able to do some work, and you store this work in the mass in the form of this potential energy, which is half kx square, and x is the stretch or compression in the spring. Okay, so now we can revisit the work and energy equation. So in the previous case, we derived this equation that T1 plus U12 equal to T2. So we derived this equation in the previous case, that initial kinetic energy plus the work done of all forces when the body moved from position 1 to position 2 is equal to the final kinetic energy at position 2. So now if we define this work, which is U12 dash, so this dash is important here. So is the work of all external forces other than gravitational force and spring force. Now we will say that we just split this U12 and we saying that if we instead of this U12 we replace this by U12 dash. So then we will end up with this equation that T1 plus V1 plus U12 dash equal to T2 and plus V2. So in this case, now this is the new work energy equation. This is the new work energy equation, and which we will be using instead of this equation, because this equation may look a bit longer, but it's always easier to use this equation in solving numerical problems than this equation here. And the reason is because in this equation you don't need to worry about uh, the gravitational forces, and you don't need to worry about the spring forces, but you will just need to calculate the work done by all external forces, which is other than gravitational force and spring force. So now you can define this equation here, that the kinetic energy at point 1, which is T1, plus the potential energy at point 1, which is V1, plus the work done between point 1 2, which is this work here, is equal to the kinetic energy and potential energy at location 2, which is this V2. And obviously we know that we can split this V1 into two, so this will be one V1G and V1E, and similarly this will be V2G, and this will be V2E. This means that this potential energy is the sum of potential energy due to gravity and potential energy due to the spring force. And similarly, this potential energy can be split into two parts. One is the potential energy due to the gravity and potential energy due to the spring. So this is the final equation that we will be using to solve numerical example. And you will see in the example that I will solve, that how to use this equation to practical problems. Okay, so this is set for today. Now we can summarize the today lecture, that we first define work, and then we also derive equation how you will calculate work. So the work done by force F during displacement dr is defined as this. So if you consider that the body is moving along this path here, and the initially it was at location A, and then it moved to location A dash, and the force F is the applied force, and the dr is the displacement from A to A dash, and the angle between F and dr is alpha. R and R plus delta R are the position vectors of A and A dash. So we can write the work, which is the differential work here, can be written as F dot dr, which is the dot product of these two vectors F and dr. And then we can write this F dot dr is F ds. So F is the magnitude of this F, and ds is the magnitude of dr, and cos alpha, and alpha is the angle between F and dr. And we can write this, that F cos alpha is Ft, which is the tangential force, into ds. So tangential force is a force which is in the direction of the displacement. And from du, if you want to calculate a force from S1 to S2, so you will just need to integrate this equation. And to solve this equation, you will need a relation between F and S. Okay, and then based on this equation, we derived a few equations for the work. So the first one was work associated with a constant external force. So when a body moves from this location to this location under the application of this P force, and which is at angle alpha to the horizontal. So we derive this equation that the work done from 1 to 2 by force P is equal to P cos alpha, which is the tangential force, into the distance or displacement from 1 to 2. Similarly, we also derive equation for the of the work for the spring force. So when you move the spring from position x2 to position from x1 to x2, and then you can derive this equation, which is minus half k x2 square minus x1 square. And again, it's negative because you are working against the spring force. Similarly, we also derive the equation for work associated with the weight, and we are assuming here a constant g. So the work done from 1 to 2 when the body move from this location 1 to location 2, was equal to minus mg y2 minus y1, and again this is negative because the body is moving against the gravitational force. And then finally we derive the equation of the this is the work and energy equation, which is the u12 equal to half mv2 square minus v1 square. And then because half mv2 square is the final kinetic energy and half mv1 square is the initial kinetic energy, which we can write is delta T, which is the change in kinetic energy. So this is the equation of the work and energy. So T1 plus U12 plus equal to T2, and then we can define this U12 dash is a work of all external forces other than gravitational force and spring force. So then we write this equation that T1, which is the initial kinetic energy, and plus V1, which is the initial potential energy, which is the combination of both gravitational and elastic potential energy, and plus work done between 1 and 2 of all the forces but other than gravitational and spring forces, because V1 and V2 are taking care of the gravitational and spring forces. And on the right hand side you have T2, which is the final kinetic energy, and you have V2, which is again the potential energy and is the sum of the of the gravitational potential energy and elastic potential energy.